Lesson 95 is the trapezoidal rule. The trapezoidal rule is a way for us to find area, which means it is a way for us to find an integral. Okay, most of the time we know a lot about integrals at this point in our calc lives. Most of the time we're going to work the integral by hand. However, there are some occasions where we won't want to do that in a calculus problem. And so I'm introducing the trapezoidal rule today. The idea of the trapezoidal rule, it's a lot like when we first started doing integrals. Do you remember when we first started doing integrals? Before we knew how to actually compute the integral and do the antiderivative? Yeah, we did rectangles under a curve, yes?
Oh, no.
Okay, so the trapezoidal rule is the idea of instead of rectangles underneath the curve, it's trapezoids underneath the curve. Now, the idea of trapezoids are going to not be exact, but more closer to exact, more precise. Okay, because they have the angle. Okay, so first of all, area of a trapezoid. Do you remember the area of a trapezoid? Okay, it is right there in case you have forgotten. But 1/2, and when I think of it, I think of it as 1/2 h times b1 plus b2. So I think of it as 1/2 times the height between the bases times base 1 plus base 2. And the base 1 and base 2 are the two sides that are parallel, whichever way you go about it. The height is the right angle distance between the two of them. Okay? So, I mean, if you want to think about... Yeah. So the idea that this is B1, this is B2, and then, you know. Ooh, that 2 went really weird, didn't it? Okay. So there's a, I don't know, maybe a more traditional trapezoid if you need that visual for yourself. Now, the trapezoidal rule. That is what I've written in here. The trapezoidal rule, I glitched. Please fix my glitch if you've already written it down. That's a huge glitch. B minus A over 2n. And if you realize, we often talk about B minus A over n. In fact, we're going to, because that's going to help us find the width of each section. But in the trapezoidal rule, it's B minus A over 2n times y naught plus 2 times y1 plus 2 times y2 plus 2 times y3 plus, it's dot, 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 because how many trapezoids are we going to break this area up into? Infinity or whatever the problem tells us to. Okay, so, and then, so plus, and then y in, so however far you go. Now, with these y values, you'll notice the first y value and the last y value do not get multiplied by 2. All the other y values get multiplied by 2. And that's because, keep in mind, we're adding up the area of a trapezoid plus the area of a trapezoid plus the area of a trapezoid, right? And as you add up the area of the trapezoids, okay, the first side, you're only going to use once. But then when you have a trapezoid standing next to another trapezoid, we're going to use these pieces twice. Each of the middles you're going to use twice, and then when you get down to the end, we'll just use it once. And I'll try and show that a little bit in the picture. Okay, so there's your trapezoidal rule. Obviously, I'm going to help you understand it, right? So let's look at example 1. Approximate the integral from 1 to 3 of x squared dx using the trapezoidal rule with n equals 4. And compare the estimate to the value obtained by using the fundamental theorem of calculus. Well, the fundamental theorem of calculus is what you guys are probably already thinking through in your heads of what's the integral of x squared evaluated between 1 and 3. But you're saying, why can't we do that right now?
Yes, it's much easier.
It is. It is much easier. There's no lies there, okay? Not an argument at all. Okay, so let's think back to if we were doing rectangles under the curve, except we're going to do trapezoids under the curve. So the curve is x squared from 1 to 3. What does x squared look like? It's a parabola. And we're looking at this parabola, excuse me, from 1 to 3. I drew the first quadrant there just because, I don't know, I can't just start at 1 with a parabola. That's just too weird. But it specifically says from 1 to 3. I'm going to label 1, 2, 3 there. So we're looking from here to there. It says with n equals 4. What does that n equals 4 mean?
That's how many trapezoids are going to be.
All right, that's how many intervals we're looking at. So we're looking at 4 trapezoids. Now, you may not need this, but do you remember how to find the width of each trapezoid if it's in a weird... What's the width of each trapezoid here? If I'm taking 1 to 3 and breaking it into 4 pieces, you're going to have a width of 1/2. Now, in case you've forgotten, do you remember doing, this is where I goofed up above, b minus a over just regular n will help us find the width of the interval? Because b minus a, b and a are my intervals. So 3 minus 1 divided by n is 4. 3 minus 1 is 2 divided by 4. So each interval has a width of 1/2. Does that sound familiar? Not as necessary on this one because if you think it through logically, it makes sense that each interval is a width of 1/2. But on the next one, you might want it. So let's go ahead and label our intervals. If each interval is 1/2 wide, then we're going to have 1. In between 1 and 2 is, I'm going to say 3 halves. It's 1.5, right? Then 2, in between 2 and 3 is 5 halves, or 2.5, if you will. Okay. Excuse me. Those are my rectangles. Or, excuse me, trapezoids. Our curve was y equals x squared. And realize I'm not even going to try and draw the trapezoids in. But the idea is that the trapezoids are, each side is on the curve. Okay? So here's a side, here's a side, here's a side, here's a side. Each of those pieces are on the curve there. We know the width of each trapezoid, right? How are we going to know the heights of each side of the trapezoid?
It would be f of the x value, right?
Okay, f of the x value. In other words, it's the x value plugged into the equation. So in this case, it's the x value plugged into the equation of y equals x squared. I'm going to set up an xy chart here. And I probably made that a little bit too close, but that's all right. So we're going to need to know all of these heights. So when x is 1, what is y? 1, because 1 squared is 1. When x is 3 halves, what is y?
9/4.
Square 3 halves, and it's 9/4. When x is 2, y is 4. When x is 5 halves, (25/4). And when x is 3, y is 9. Okay. I've kind of done all the prelim work, I think. And I guess, I don't know. I don't know if it's necessary to put this in here or not, but the idea that when x is 1, that y value has a height of 1. When x is 3/2, this was 9/4. Okay, those are the y values we just found. Okay, so with each of those x values, we need to know those y values and what the heights are. We did that by using the equation. I'm ready to set up my trapezoidal rule. I'm just using t equals because it's a trapezoidal rule. Out front, it's b minus a over 2n. So b minus a is going to be 3 minus 1, which is 2, over 2n. So 2 times 4, which is 8. I'll clean that up in the next step. Now, why not? What is our first y value? Our first y value was 1. So we're going to have 1 here. Plus, now we're going to do 2 times the next y value. What's my next y value? 9 over 4. And do you see why we're doing 2 of it? Because it is the height of the right side of this trapezoid, and it is the height of the left side of this trapezoid. So that's why there's 2 of all the ones in the middle. So 2 times 9/4 plus 2 times 4 plus 2 times 25/4 plus, now down to the last one, which is just a single 9. Because when you get over here to this last one, we're only using this right side of this final trapezoid once. Okay, from here I'm just going to do the cleanup. 3 minus 1 was 2, over 2 times 4 is 8. 2/8 is 1/4. 1 plus 2 times 9/4, how about if I say 9/2? Plus 8 plus 25/2 plus 9. Okay. My brain says 9/2 plus 25/2 is going to be 34/2. I'm just taking my 2 fractions, right? 34/2 will be 17. Plus another 1, 8, and 9, which is another 17 plus 1. 35. However you do it, right? Maybe you got a common denominator for everything. I did not. 1/4 times 35, I read it as 35/4. As a decimal, 4 goes into 35 8 times, with 3 remaining, so 8 3/4 or 8.75. Now, have you done the actual integral? It said to compare the estimate, yes? So let's compare the estimate and see how close it is. So when it says use the fundamental theorem of calculus, fundamental theorem of calculus, I probably haven't used that vocabulary enough with you. Fundamental theorem of calculus part 1, which is what we know right now, is just evaluating an integral. So the integral from 1 to 3 of x squared dx. Well, the integral of x squared is 1/3 x cubed from 1 to 3. We plug in 3. 3 cubed is 27. Divided by 3 is 9. Minus 1 cubed times a third. So 9 minus a third. Well, my brain says 8 2/3. In my notes, I've written down 26 thirds. But in all honesty, I like 8 2/3 because 8 2/3 is 8.6 repeating. Is it close? I mean, 8.75 versus 8.6 repeating, that's pretty close. Obviously, it could be exact, so it's not 100% close, but okay. Questions on that one? And notice, technically that one could be done without a calculator, right? I know some of you may have picked you may have picked up a calculator and used it for pieces, but in all technicality, that can be picked up and done without a calculator. Okay, one more example, right? I just have the front two. Yep. Approximate the integral from 3 pi over 2 to 2 pi of cosine x over x dx using the trapezoidal rule with n equals 4. Well, what do you guys know about the curve cosine x to x? We know cosine, right? But cosine x divided by x?
You divide it by x, it's a whole.
Except that we're not on the 0 interval. So, I have a graph sketched here, so I must have done it. Hello. Yes. Yes. For you. This is for none.
Oh.
Do you have to have an answer right now?
Yes, for none. Yeah, my dad's gonna bring it later.
Yep. Fine. Let me guess. Lack of note.
No, I just have my dad's bringing the payment to receive your trip, and she asked me to make sure I was
see your
actually.
Oh, and you were here this morning when I thought maybe it was a question about an excused absence this
Oh
morning.
yeah. No.
Okay. Now, what window am I on?
I had the same window.
So whatever it is, I graphed it last in calculus.
Okay. I had the same window.
I'm like,
I changed it back, but I had the same.
what window is this? Okay, so what I was gonna do is a Z trig, but in all honesty, what window do I need to be on here?
That window.
We really only need to see 3 pi over 2 to 2 pi, right? So in all honesty, I'm going to go here into my window and by hand change my x-min to 3 pi divided by 2, and my x-max to 2 pi. And then probably should have changed, well, it's hard to tell here. It's running very close to the axis, isn't it? Now, we can't really tell, so what I'm going to do, obviously, do I really need to go all that way up and down? I think I saw my y min and max were at -4 and 4. I'm going to go -1 and 1. And it appears I could have even zoomed in a little bit more, but basically this curve is just running up and above the x-axis, isn't it? Okay? That's the gist of what the curve is. So, on my curve, I didn't even graph the whole thing. I just graphed the idea that we're starting at 3 pi over 2, and we're going to 2 pi. It looks like, according to what I drew here, that it is a 0 at 3 pi over 2, but I don't know that for sure. Now, we wanted 4 intervals, yes? How wide is each interval? And this is where last time it was
Be 5
doable to say 1/2. This time,
5 pi over
what'd you say?
5 pi over 8.
No. So if I do b minus a, 2 pi minus 3 pi over 2, divided by n, which we are going with 4 intervals again. What is 2 pi minus 3 pi over 2?
That's just pi over 2. So it's pi over 8. Dang it.
So 2 pi minus 3 pi over 2 is pi over 2 divided by 4. Pi over 2 times 1 over 4 is indeed pi over 8. So each interval is pi over 8 wide. Fun numbers. Now, since we're talking 8s, here's my thought. Let's change 3 pi over 2 to 8s. Because I have to talk all 8s. I can't just talk 8s on some things. I have to talk all. It's all or none. So 3 pi over 2 is 12 pi over 8, correct? What's 2 pi? 16 pi over 8? And if we are breaking this up, if you recall, into 4 pieces, right? Well, if this is 12 and this is 16, what are each of these pieces? (13 pi over 8, 14 pi over 8, 15 pi over 8, and 16 pi over 8? It's doable, right?
Doable, yes, but doable.
I never said, did you hear the word enjoyable come out of my mouth for that? I did not say enjoyable. But I'm trying to give you the tools here, right? Like, that kind of freaks me out. Like, oh, I have to divide this by 8? What? But if you put it into 8s, and notice it's set up to work out nicely. Now, if you want to go ahead and do your XY charts, you can. It's kind of up to you here. When we do this XY chart, first of all, what's the graph you're plugging this into? Cosine x over x. And the numbers we have to use, the 12 pi over 8, which I'm going to go back to saying 3 pi over 2, 13 pi over 8, 14 pi over 8, 15 pi over 8, which technically 14 pi over 8 could reduce, but it's not a big deal. 15 pi over 8 all the way down to 2 pi. Now, some of these you could do by hand. You technically could do the cosine of 3 pi over 2 divided by 3 pi over 2. What is the cosine at 3 pi over 2? Or quadrantal angles, if you please.
Oh, 0.
It's 0, isn't it? And 0 divided by anything is going to be 0. Now, these others, do you know the cosine of 13 pi over 8?
None of the tops.
And are we supposed to know it? No. So what do you have to do with the rest of these?
Yes.
Calculator.
We would trace each race.
Put in our numbers.
That's true. You could. Since you do already have it graphed, you could put in trace and type in, for instance, 13 pi divided by 8. Or you can just plug it in normally. I have 4 decimal places written down in my notes. .0496. The 6 will tell the 49 to go up to 50. If I now hit trace again and put 14 pi over 8 in. 0.1286. Hit trace again and put 15 pi over 8 in. 0.1568. And if you put 2 pi in. Yeah, mine's not letting me to because it's at the end.
Boundary.
It's the boundary. If you think about it, cosine at 2 pi is 1. And so it's going to be whatever 1 divided by 2 pi is.
1592.
Yeah. 1592. Okay. This is taking longer than I thought it would. Fill it in. Out front, I'm going to have b minus a over 2n. So 2 pi minus 3 pi over 2 divided by 2 times 4. And then, in parentheses, the first time we just put the first y value, right? So 0 plus 2 times each of the next one until we get to the last one. So it's going to be 2 times 0.0750 plus 2 times 0.1286 plus 2 times 0.1568. Then when you get to that last one, you're just adding it by itself, so plus 1.1592. Yes, I ran out of room. I went on to a second line. Two pi minus 3 pi over 2 divided by 2 times 4. Well, really, you can just think about it. It's the pi over 8 from earlier times 1/2, if you will. So that ends up being pi 6 over 16. You end up doing some math on the calculator in there, right? Do you want my math or are you doing your own math? I have written down 0.88 before I multiply it there. So I have written down as 0.1728. Or if we do AP style and do 3 decimals, 0.173. You do. Hey, I was nice. I didn't give you homework over spring break.
I know, I was really stressing about that. Like, I
You
just
know,
feel like
Shively walked in and was like, hey, did we have
Okay. Number 8 becomes number 7 from lesson 93. And you're going to skip parts C and D on number 6. Not skip number 6. Skip parts C and D on number 6. Does that make sense?
Okay.
Let's go skip 6CD.